problem we have, we are given a Ferris wheel that is coming from rest to its operating speed of half a rotation per minute. And so what we're first going to do, we're trying to find the amount of power it takes for the motor to do this. And so we're first going to say that power is equal to work divided by time, which is its definition. But then due to the work energy theorem, we can actually see that work is equal to the change in kinetic energy. So power is change in kinetic energy over time. And to do the change in kinetic energy, we are going to take the final kinetic energy, which is 1/2 I omega final squared, minus the initial kinetic energy, which is 1/2 I omega initial squared. And all of that divided by time is going to equal power for us. But what we can see is that there's actually no initial speed because the Ferris wheel is coming from rest. So this is 0. Now to find I and omega final, we can come over here, and you see that I, the inertia of the Ferris wheel, we can assume that the Ferris wheel is a thin circular ring, and so I is equal to mr squared in that case. So I is equal to the mass of the Ferris wheel, 20,000 kilograms, times the radius, which is 96 its diameter, divided by 2 squared. And that is equal to 46.08 times 10 to the 6th kilogram meters squared. Then to find the omega final, we need to turn it from rotations per minute, to radians per second. So omega final is equal to 0.5 rotations per minute, and we're going to do unit conversion here. So 1 rotation is equal to 2 pi radians times 1 minute, which is equal to 60 seconds. And from this we find that the final speed is 0.05236 radians per second. Yes, and then we plug back both of those into this equation. So power is equal to 1/2 46.08 times 10 to the 6th times 0.05236 squared divided by 15 seconds, which is given in the initial problem. And we find that the total power required is 4.21 kilowatts. And that's your final answer.